Okay, hi everybody, welcome back. Hopefully today there's no alarms or sirens or evacuations. So we're going to continue with linked lists, and we're still just inserting nodes into the lists because we only got up to creating nodes and putting them at the beginning last week. As always, there's links to the lecture code. Again, I've probably reminded you about this a million times, but this week you do have your chance to go and do a week 8 lab exam. It's just really a good opportunity for you to see how you're going with the content that you've had time to really learn. So arrays and stuff like that mainly is the focus. And also see what the exam environment's like. So when you do turn up to the final exam, you'll be able to focus on the questions rather than, oh, how do I submit and how does, where do I find this and that? You'll be familiar with the environment. So please turn up if you possibly can. Email us if you can't, we'll try and organise something for you. And it's not worth anything but 1 mark for just turning up and submitting something. We want to make sure that when you do go to the exam, you'll know how to submit your work, all right? We're not going to mark what you work, we're not giving you marks for how your code actually works this time. Obviously in the final exam, yes, we will. Any questions about that? Okay. Oh, do you mind unplugging it again? Sorry. My hands are too, I don't know. Thank you. Okay, sorry. Okay. Shh. Hands up who's had a look at assignment 2. Okay, lots of people, that's amazing. How are people going? Have you been able to sort of get started on the first 2 stages? No? Still a bit confused? Maybe? Oh, does it have, oh, okay. All right. Hopefully, I mean stages 1.1 and 1.2 kind of thing. Yep, that's what I meant, yep. Okay, so even if you're not on top of linked lists, which we've just started, stage 1.1 and 1.2, I don't believe have actual linked list operations. But also the other thing you can do at this point, if you don't feel confident with linked lists, is obviously focus on tutes and labs and lectures this week, but also every assignment you need to fetch the code, read the spec, play around with the model solution, see what it's supposed to do. So please, if you haven't started, and this is to anyone watching at home as well, start on that. That's a huge step. Think about what you've got to do. Then when you are in your tutes and labs this week, you'll be able to think, oh, wow, yeah, that's what I probably need to do in stage 1.3 or whatever it is. The other thing is, as you might have found out with assignment 1, please be quiet. As you might have found out with assignment 1, help sessions do get busy towards the deadline. Did anyone find that out personally? Anyway, so the sooner you get started and get help if you need it, the better. The other thing is, we often in this course, and actually probably lots of courses, see that sometimes people are over-relying on ChatGPT a bit during the term, which can be problematic because, you know, if you're really overusing it and completely getting your solution, it might match other people's solution and get flagged for plagiarism. But even if you're not using it to that extent, just be aware that in the final exam, you're not going to have any kind of ChatGPT kind of thing. So you really need to get used to doing things and debugging and thinking things through, you know, without using that. So think about that as you do your labs as well. Just make sure you're getting that practice programming and debugging yourself. All right, there will be some revision sessions this week. There's been an announcement on the forum. You can sign up and vote for the topics. I think topics like pointers and malloc are looking popular on there right now. So that's on this week, online 2 to 4. Revision sessions aren't recorded. You do, you know, need to turn up if you want to sort of see what's happening there. All right, any questions with any of this admin stuff? All right, now we started linked lists last week in our Wednesday catch-up lecture, which was because we didn't get to do our lecture last Monday properly. And that's where we looked at linked list basics, creating nodes, printing a list, inserting nodes at the beginning. Now, if you haven't watched that lecture yet, and potentially even if you have watched that lecture, today's lecture might be tough or a bit confusing, all right? Linked lists take a bit of time to get used to. You'll be practicing them this week in shoots and labs. All right. So hands up who wants to get into linked lists now versus doing sort of a Kahoot on pointers and malloc and some basics. So hands up for linked lists right now. Hands up for Kahoot on malloc and basics. All right. I might do the Kahoot just so we can clarify anything that people aren't aware of before we go into the linked list, which rely on them. Okay. It'll just be a short one. All right, so I'll just wait a few minutes for people to join, and this will help me see what people sort of know and don't know in terms of the fundamental mallocing and pointers and stuff. I won't turn up the music any louder. We need some quiet after last week. Actually, maybe I will. All right, it's a little bit up. Yeah, sing along if you want to this Kahoot song. Okay, I'll just wait one more minute for anyone else to join. Okay, let's get started. this first one, there's no right answer. This is just about me wondering. Okay, so the majority of people are not saying they're very familiar. Yeah, pointers take time and practice. People don't feel like they're on top of them straight away, so that's pretty normal. But most people are feeling at least moderately or a little bit okay with them. All right. I should get rid of this so you can see it properly. Okay, so most people know we use ampersand to get the address, just like we do with scanf. Okay, very good. We use the star when we're dereferencing it, not getting the address. And if you've got questions, please ask. All right. And people are going really well. Just quickly, just a quick reminder, we've got a normal variable called num, which has the value 5.2 in there. Then we've got a pointer, and we're putting the address of that into this variable. So we just think of this as pointing to this variable here. And when we dereference our pointer, it means we're going to that value that it's pointing at, or to that memory location that it's pointing at. So we're getting the 5.2 out. 5.2 plus 2 equals 7.2. And again, we're storing it back at star numpy. That's where numpy is pointing to. So we're overriding that with 7.2. And this is the whole thing about pointers. We can indirectly access other variables. So now when we print out num, it should give us 7.2. Okay, any questions? Right. Okay, people are going very well. Okay, and yeah, most people got this right as well. So here we've got, sorry, I know a lot of people did get it. We've got a struct called me and a pointer that's pointing to that struct because it's got the address of me in there. Now with pointers, and I've said this before, you can dereference them and then access the field, but you would have to do it like this with the brackets in the right place. So the easiest way to do it is to just use arrow and then set it like that, which, you know, most people did get, so that's good. Yay. So yeah, if we've got local variables, which are variables declared inside a function, they're stored on the stack. Okay. Hopefully this question makes sense. Okay, so what does this question mean? What's going on? It's basically saying if we're passing x, a, and p into a function, you know, which of those can the function actually modify the original copies of? So remember, if I'm passing in an integer to a function, it's just giving a copy of the value inside it, which is 5. If we pass in a struct, it's just passing in a copy of that struct. So the function itself will have its own versions of x and p. And if it modifies them, it's modifying these versions. It's not modifying the original data in the main. So is everyone happy with that? We pass in copies of things. And that would have happened in your first assignment maybe. You might have had structs and maybe you were trying to change them in a function and they weren't being changed. Unlike arrays, if we pass in an array, what is really happening is this is really just the address of the array. So the function has the address of this original array. Any changes get made to that original one, right? So if we want to be able to change the original struct or integer or anything else really except array, we would have to make sure we're passing in the address of it. With arrays, that's just done by default. We don't need to do anything special. Does that make sense? Okay. And the pictures are irrelevant. They're just pictures I like most of the time. Sometimes they're relevant if they've got code in them. Yay! Malloc, we get memory on the heap, which is very important. Even more important is to understand, well, what does that mean if it's on the heap? But I think that might be the next question. Yay. So yeah, two things. If we put our variables on the heap, we can actually do mallocs while our code's running and keep asking for more and more memory. We don't need to know in advance how much we're going to use. The other thing is, if it's on the heap, it doesn't automatically get destroyed when our functions end. It can stay there until we decide we're done with it. Okay, excellent. Any questions? A couple more. well, people really are going well. So yep, we use size of to find out how many bytes is in an int. If we want 5 of them, we multiply it by 5. And it's going to return an address. We store addresses in pointer variables. Very good. Okay, so this was all fine. It just didn't free after a malloc, which means if we compiled it and ran it with DCC leak check, it would complain at us. Okay. You've got to type this one in yourself. Okay, so yeah, we want the size of the struct node. Size of will tell us how many bytes are in that struct node. Just be careful, don't put a star in there. I can't do this. Yeah, don't put a star in there and make it a pointer, because that's kind of like asking what's the size of this address I've written down rather than what's the size of the house. They're very different sizes. We want the size of the struct because we want to know, we want enough memory to store everything that needs to go in the struct. That's a very different size to the pointer, which is just an address. Okay, because that's a common mistake. All right. Timeless elk, you're going very well, whoever you are. Yep, so basically very similar to what we did. We find the size of the struct node. We give that to malloc. Malloc gives us a chunk of memory. Malloc always returns some kind of address or null if it fails, and we have to store that in a pointer of the correct type. All right. I think the last question, a linked list one, it's an easy, well, it's not easy if you don't know linked lists. Okay, so a linked list has no nodes in it at all. It just has an address with null, which means there is no address. There's no nodes in our list. Okay, that's our empty linked list. All right. Actually, I think people are doing better with this stuff than they wrote in that first little survey. People are going well with pointers, it looks like. All right. If you come in the first 5 or whatever, feel free to get chocolates either now or on the break, up to you. And you can choose them or pick whatever ones you like. All right. And if you're at home and you want to screenshot it and come in and ask for them, that's good too. All right. Okay, so now that we've done that, let's actually start using all those concepts and working on linked lists. So we'll do a bit of a recap of linked lists, then we'll insert at the tail, like the end of the list. Then we'll try and insert nodes in the middle of the list and stuff like that. But today, basically, it's about how can we create these lists and add more data to them. And what are they? Now, I did talk about this already, but just to remind you, because typically people need to see these a few times before they're on top of them. So with an array, we would have all of our data in one chunk right next to each other, every value after the other one in order. And we can easily write a loop, a for loop or a while loop, to go from index 0 up to the last index and traverse the whole array. We can easily as well just use an index and go exactly to one particular element that we're interested in. With a linked list, they're stored in a way where they're scattered around in memory. They're not all together. And we don't really know where they all are, like up front, or where they're going to be. So it's very hard for us to jump to particular. We can't just say, let's go and jump to the 10th element in this list. We've always got to start at the beginning and go one by one and maybe count and go, okay, this is element 10, yay, we found it. So we say that we don't have good sort of random access in the linked list. So in this example, we're storing the value 13, 17, 42, and 5, but we can see, imagine this is just a drawing to imagine what it might be like in memory. It's scattered around in different places on the heap. And instead of just storing the values that we actually want to store, we've got to store extra addresses, because the addresses help link up the list. They tell us where the next pieces of data are. So actually, I'll move to the next slide. So it actually stores structs, and we often call these structs nodes. So your linked list will know the address of the first node in the list. And that first node and all the nodes will have some data in there. Now, in the list we look at today, we'll just be using ints because they're just easy. Obviously, in the assignment and in other applications, you'll store whatever data in there that you want, like songs or whatever it is, food, I don't know, whatever data it is that you need to store. But we've got ints in here, so that's our data. But as well as the data, what every linked list will have is the address of another node of the same type. So this node tells us where to find the next node. So I can go, okay, the list itself will have a variable keeping track of the first node, but then the first node knows where the next node is. It's got this field here that's saying, okay, the next node is at address 5C. So if we go to 5C in memory, we're going to find another struct. If we look at the data field, it has 17. If we look at the next field, it tells us where the next struct is at address 48. When we go there, we find our 42, and we see that the next struct is at address 3C. We go to 3C, we get a value 5, and then it says the next address is null. And null means there is no address, which means in a linked list that there's no more nodes in the list. Yep. The question was, does the head typically have data stored in it?
Or is it just like an at pointer?
In the way we're doing things, the head of our list is just the address and it's just a pointer. You can have variations on all these things where you might have a whole struct that contains the address of the first node and other things as well. It depends, but yeah, so it depends. But the way we're doing it, we've just got the address of the first element. But yeah, that could be embedded in a bigger struct as well. So yeah, this is the address of the first element here. So this is imagining we've already created this linked list, but that's how we have to work through them. We can only ever start at the beginning and go one by one because each node knows where the next node is. All right. So yeah, this is our struct node list. It's just an address that eventually will have, you know, the first node's address in there. And often we draw them something like this, because we'll be drawing these a lot when we're trying to write our programs and thinking about what we're linking up and what we're doing. We won't always make up fake addresses like I do at the beginning. Eventually we'll just be drawing boxes, but this is just showing us that the head really just shows the address of where this first node lives. This first node shows the address of where the second node lives, etc. And unlike arrays, we don't go and ask for a bunch of memory and guess how many things we're going to store. We just start off with an empty list with nothing in it, and it just is initialized to be null. There's no address of the first node. There is no first node. And then as our program's running and we need to store stuff, we start mallocing stuff and connecting it up to our list. So the other thing is to be aware of, for this to be useful, we want our nodes to live on the heap because we want functions to be able to create them and destroy them when we want them to be created and destroyed. And we don't know how many we want in advance. So this is a perfect thing to use malloc and the heap for. So if I do want to create a node, and we did write a function called create node, but this is what it kind of did. Well, we've got to do a malloc. And the malloc creates this chunk of memory of the appropriate size. And then malloc returns an address. We're going to store that in our head or list or whatever we've called it variable. And remember, if I've got a pointer to a struct, I use arrow to access the members inside it. So I could go and set the data to be 21. In this case, there's no more nodes in this list. I'm setting the next to be null as well. So here I've created one node and my list is pointing to that node. So this is a linked list with just one item in it. Yep.
So when you typically insert it into like the linked list, you would do that outside of the function you're creating, right?
Like where would you do this?
Like when you insert it, when you want to insert it in a position, you do it outside the function.
If you want to insert a node into a list, would you do it outside the function? Well, it's like everything. Like you could write insert and then you could have all this code in there, but it's much nicer if you make a function that does this create node that you can just call. So you're not, you know, it's not cluttering up the insert.
No, I mean like after you created this like part of it, this header, this node, you would position it where you want to after you call this function.
Oh, right. So if you create a node, then you might want to position it somewhere else and then hook it up. Yes, that's true. In this case, we can't put it anywhere else because there's no more nodes. But in the next example, that I think is exactly what you're kind of asking. So when you've got nothing in the list to begin with, there's nowhere for the node to go except right at the head of the list. But just say we want to add another node to our list. At this point, we could put it after the 21. We could put it after this node and connect it up there. Oh, I'm going the wrong way. No, I'm going the wrong way. Okay. We could put it after the 21 in the list or before it. Now, today, I'm going to add a node before it. And we did look at this last time. So the first step, I'm doing my malloc I've made a variable called new node, but I'm doing a malloc and creating this new node here. I'm setting the data inside to be 99. And in this case, I want to connect this to the beginning of the list. So I want this node that has 99 in it to be the first one in the list. And whatever else is in the list, I want it to come after it. So I'm putting this connection in here, right? So in this case, I'm wanting this next field to be linking this node to this node here, right? So I want the value in this fictitious example, 88 in there. But when you're coding, you don't know these addresses. What we're going to just say is new node next equals head. So that's setting this field here to have this value in there. But really, you want to be thinking that the thing that comes next after this new node is whatever is already in the head of the list, right? We're putting it before the head of the list. After it comes this head of the list. So that's how we could connect it up. Once we've done that though, I'll go to the next slide. Once we've done that, we've connected this new node to the other node, but the variable that's keeping track of the first node in the list is now wrong. This isn't the first node anymore. The new node is. So we need to update head so it knows where the start of the list is. So we can just say head equals new node, right? What that does is it copies the address from here into here, but you just think of it as, well, the head of the list is now that new node I just created. That's what the head of the list is now. Head of the list just means start of the list. Does that make any sense at all? Does anyone have any questions? Yep.
Can you only add stuff at the beginning and the end? Can you add them in the middle?
Yeah, we will see today. Somebody just asked, can we only add at the beginning or the end? No, we can add anywhere we like. And no matter where we add it, we'll do a malloc, and then we've just got to change all these pointers around. So it's just a matter of finding where you want to put it and changing the pointers around. So we should see that today. Okay, so that kind of code we just looked at, we put this inside a function called create node. It does the malloc. So we've got new node, which is just, some variable that's doing a malloc. Now we checked if the malloc works. Malloc might fail and have no memory left. It returns null. When we're using this function, we would pass in what value we wanted to store and what address we wanted it to point to. I'll just put, question marks here. And we just go and set that inside the node. Whatever address it wanted to point to, we put in there as well. And then we return it. So this is just really creating a struct and setting data inside it. Okay. And then we don't have to keep retyping this stuff in later on. It makes it easier for us. Now, I'll just go back to the code we did the other day. So we use this create node to insert stuff at the beginning. And I'll just remind us of how that works, just in case. We've got the head of our list, which is just null. And here we're creating nodes from 0 up to 9. So the first node we create will be one that has 0 in it. So create node will do a malloc. Actually, I shouldn't draw it so big. And it's going to pass in the head. The head in this case is null, and it's going to set this next field to be null. And this is our new node. Right? And then we're just saying, well, actually, the head equals this new node. So now the head won't be pointing to null anymore. It'll be pointing to this new node. That's our first node. Then when we go through again, I will be 1. We're calling create node. and that's returning something to new node. It's putting the value 1 in, and it's setting this next value to point to where the head is pointing. So this new node will be connected to the head. So whatever this address was, it's also going to point there. And then again, we do this line here to say, well, now the head of the list is this new node. And we do that again and again and again. We create a new node. We're putting the value 2 in it, and we're connecting that up to what is the head of the list, which is this node here. And then we're saying, no, this is the head of the list now. And we do that, we end up with the list that has 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 in it. So when you're always inserting them at the beginning, it's going to look like it's, you know, in reverse order to what you did. The one you just inserted will always be at the beginning. All right, so this code here is adding them to the beginning. Now, adding them to the beginning is the easiest because we know where the beginning of the list is. We don't know where the end of the list is, right? We'd have to go and find the end of the list and then add a node on, but we're going to see that in a minute. The other thing we wrote was printing our list. So obviously we don't want to manually do this, we want a loop. So we looked at how we could print out a list or traverse a list from the beginning to the end with a loop. So when we're programming with linked lists, we've got a variable that's keeping track of that first node. We just need to be careful that in whatever context we're in, we don't overwrite that and then we don't know where that first node is anymore. So it's like losing someone's address, right? So what we often do is we create another pointer that we can move around, but we leave head still pointing to that first node. So here I've got current equals head. This is just a pointer. It's pointing to the first node. But then I want to move it, I want to have some kind of loop and I want to move it on to the next one. I want current to point to here. Well, the only way we know where the next node is by looking at this member in this struct. So if I've got a pointer to this struct, current arrow data gives me what? If I've got a pointer here, current arrow data gives me what? Yeah, 13. Current arrow next gives me the address of the next struct. Right? That's what's stored in this member. So I say current equals current arrow next. And that has the effect of, you know, setting current to be this address here, which moves it on to the next node. Again, current is pointing here. Current next is this value that points to the next node. So I say current equals current next. And it moves it along again and again. Okay, now when I get to here, current arrow data is 5, current arrow next is null. So when I say current equals current next, current will now be equal to null. Does everyone agree? And once current's equal to null, we are no longer pointing at any nodes. We've gone through the whole list and we've gone past the end of it. And we're kind of done. So our loop will sort of stop when current equals null. We'll start at the head, we'll stop when we get to current equals null, and we'll keep saying current equals current next. And this is sort of the pattern that you use when you're traversing the linked list. So we did this same thing to print a list. Again, I'll just draw it again, just with boxes. It's not really the same list, it's probably different numbers. We're given the head. We'll make another pointer called current that points to the same place the head does. And we check, is current equal to null? No, it's got the address of some struct. We print out the data, which gives us 5, and we say current equals current next. It moves it along to the next one. So now current is pointing here. That's not null. We print out the data. We say current equals current next. It moves it along to the next one. That's not null. We print it out. We move it along to the next one. Now current is equal to null. There's no more nodes. And this finishes the loop. All right? This is going to be code that you write something similar to this again and again and again when you're working with linked lists. All right. Any questions about this? Yep. Oh, you can't go backwards in a linked list like this. There's a thing called doubly linked lists where there's pointers both way. We're not going to do that here. So for us, we can't really go backwards. To go backwards, we'd probably have to count how many things are in the list and then sort of go through the list forwards to get to, anyway, it would be awful. All right, so, oh, yep.
What's like, because I've seen certain cases where they'll do like current next in the while loop or current next in the while loop. What are those about?
Oh, someone's asked about, I've got current is not equal to null. Sometimes our stopping condition might be a little bit different, and we're going to see that next. The word next starts sounding weird. Yeah, and so the code that we wrote the other day, if we compile it, I've got the loop. Each time I print the list before I've even added anything to it, and then I add a node, and then I'm printing it, and we can see that we got the end list, you know, it looks like it's backwards because we inserted them all at the beginning. So what we're going to do is, how do we add nodes to the end of a list? So that's what we're going to do now. Now, in order to add a node to the end of the list, the first step is finding that last node in the list, because that's what we want to connect it to. Once we've found it, then we just connect up those pointers. So that's what we have to do. How do we find the last one in the list, do you think? Yep.
While loop, while current is not equal to none, so we'll get the...
Well, yeah, it's very similar. It's a similar thing. We start at the beginning and we do current equals current next, etc. Now, if we go all the way to current equals null, we've lost that node that we need. We need current to point to this last node. But if we go to null, we've gone on too far. We want to stop here. And this is exactly what you were just asking before. How do we know we're at this last node?
Current next equals null.
Yeah, when I'm here, current next equals null. If I'm here, it doesn't. That's not null, that's not null, that's not null. Current next is null. So we have a slightly different condition. We don't want current to be null because that is not pointing to a node anymore. Current next is null. That's our last node. So we just use a loop until current next equals null. Now, once we're there, basically we just want to create another node, and this new node will be the last one in the list. So it's going to point to null itself. But now we want to take this one and connect it up, right, to this new node that we create. So we want to change this value here. What's this value here called? How do we access that in our code in this scenario? So if current's pointing here, this would be current next, right? If current's pointing here, this is current arrow data, current arrow next. We'd want current arrow next to just have the address of this new node, because that would be then linking it up. So we create our new node. It's not connected to the list yet, but now we say current next equals new node, and it links it up we want this one to point to this new node. And that's how we add things to the end of our list. We find the last node and we just modify this field here, which points to the next node in the list, and that's going to be our new node that we just created. And this new node, it's going to be at the end, so we would have initialized this to have a next value of null. All right. So we won't have a break yet, just give me about 5 more minutes, then we can have a break. So when we put all that together, we've got, again, I'll draw it as well. We've got the head of our list. We've got current, which is pointing to the head. And we're checking, is the next one null? No, this is pointing to another node. So we move along, current equals current next. Is the next one null? No, we move it along, current equals current next. Is the next node null? Yes, we stop. Our loop stops and current is pointing to this last node. We then create a new node. So our new node, we know that create node's going to malloc it and it's going to set the data. So if this said 10, it'd put the value 10 in here. It sets the next one to be null. And then we say current next equals new node. So current next won't be pointing to null anymore. It'll be pointing to this node here, which is very messy, but here's our list with this node, then this node, then this node, then this new node. Okay, so that's what that last line is doing, connecting it up. And oh, it says at the top there's a big bug. And there is, but everything I'm telling you in this drawing is true though. The bug is a different case. Does this make sense? Can anyone think of what situation this might not work? Well, first of all, before we go to the break, let's just try it. Insert at tail. I'm making my current equal to the head. I'm saying while current next is not equal to null.
If there's no nodes already, it's just already a null pointer and it can't point to any of the...
Yeah, the problem will be, that's exactly right. If there's nothing in the list already, the code we've written will make things crash. So I'll show you what happens. That's one of the bugs. So this is the code that's finding the last node. Then we want to create a node, and we could have created that at the beginning. Node, new node. We've got our create node function. We know it's going to be at the end. We're going to set its next field to be null. And now we're just saying, I found that last node, that's called current. And the next one, oh, it's bad that on my laptop, my X key, my 1 and my exclamation mark key don't work very well. But I still prefer this keyboard to this one. Anyway, so if you wonder why I'm suddenly going like this, that's why. But I'm typing X a lot today. All right, the new node will come after this current one. So current next equals new node. Hopefully that's what I just told you before. And up here, I've already got some code that's doing a similar thing. I've got a new list called head2. And in this time, I'm using my insert at tail function and printing it each time. I'm still running the other code. So I should end up with a linked list, you know, that has values in one order and then another linked list. what am I doing? There we go. So this is the linked list we did before, adding it at the beginning. This is the code we just wrote. And the error that we're getting, and we'll talk about how to fix all this after the break, but the error that we're getting is saying you're accessing a field via a null pointer. And it's telling us where we're doing that. It's saying on line 77. So if I go to line 77, it's happening here. Why is that? Well, if I've got nothing in my list, my original list will just be equal to null, right? When we've got nothing in our list, it's not pointing to anything, it's null. So that's in the main. It's going to pass null into here, and head in this function will be equal to null. We then initialize current to be null. And now what we're doing is saying basically null arrow next. So this is called dereferencing a null pointer. When you do current arrow next, you're trying to go to the address that's in current and then access data inside it. You can't do that with null. If you ever try and go to the address null, your program crashes. So that's what we're doing here. And our program crashes, as we would expect. This is going to happen to you all the time. In your assignment, if this doesn't happen to you at least once or twice, I would be very surprised. And you've got to look and think, did I handle that situation where I had an empty list? And you know, the empty list is the easiest one to really, because there's nothing in it, but it's the one that will break things. So what could we do to fix this function? Yep.
Store the head and then return it.
That's something else we do have to do, store the head and return it. But how do we fix this null pointer problem?
So can you check if the current is already null by putting in an if statement?
Yep.
And then if it is null, then don't try to attach it to the head list.
Well, yeah, if my list is already null and there's nothing in it, where do I want to put this new node? Yep. Yeah, if there's nothing in the list already, the head of the list will just be this new node, right? And this, now the list will have this one thing in it. And basically putting it at the head of the list is also the end of the list because there was nothing else in there. So we can just say head equals current, otherwise we go, oh, we don't do that. Otherwise we go and find that last node. We don't want to do that if the list is empty and there is no last node. So this, I hope, will stop the crashing. It doesn't crash. Does it work? No. There's no data being printed out. There's another bug. I'll quickly tell us, then we can go to break. But remember, we've got a variable up in the main that I've called head2, which is a terrible name really. And it's got the value null in it, right? Because it's empty. We're passing that into here. And in this function, we've got a variable called head that has a copy of that value null. Now in here, we say, oh, well, yes, current is equal to null. And, oh, I did this wrong anyway. This should be the new node. But we would still have this problem. Okay. And I'll clear this. So we work out that the head and current were equal to null. And we create our new node. What else have I done wrong? I'm making mistakes I'm not trying to make now. Control X. I should create the new node first now, because I'm using new node up here now. Okay, Let's try it again. Down in here, I've got head equals null. I've got current equals null. I've got my new node variable, which let's assume malloc works. And I've got my new node. I'm checking, is current equal to null? Yes, it is. If that's the case, I know I've got nothing in my original list. So I say head equals this new node. And that's all lovely. I've created a linked list. Head is pointing to this new node. I've got a linked list of size 1. But then what happens? Basically, this function finishes. What happens when this function finishes? All the variables from, all the normal variables that aren't malloc data will be destroyed. And we'll still have this node on the stack somewhere, on the heap somewhere. But what does our original variable back in the main still have in it? So our original variable, head2, back in the main, it still has null in it. So if we go back here, this variable has null in it. We've never done anything to change that. So what's happened is we've inserted the node into the list, but we need to tell the main function where the head of the list is now. It still thinks the head of the list is null and there's nothing in the list. Does that make any sense? Yep.
So in the case where you're just adding like a tail, but the head is not null, that the address of the head doesn't change, so you don't really have to return in that case, right?
Someone made a good point. So it's only in this one case, in this situation, where the head will change when we're inserting it at the end. When we're inserting it, if there's already nodes, the head of the list isn't going to change, but we have to do the same thing for the whole function. So what we'll do is, in here, we will return that head in case it's changed. Okay. And I'd have to change this up here. So this is saying we're returning the address of a struct node or a pointer to a struct node. Now, if I do this, because this is what people might do as well, it's still not going to work because when we call the function, we've actually got to use that return type. We've got to say head2 equals this. So now inserted tail is going to add the node to the list. It's going to pass back the address of the head of the list in case it's changed. And now our main will be able to store that variable and know where the new head of the list is. Okay? So the function could be changing the head of the list. It has to return that so the head knows where it is. So if we do all of those things, we should be able to insert at the tail. So let's have a quick break. When we get back, I can just go over what we just did, just to recap it a little bit, and then go on and insert things in the middle of the list. Okay.
So this is how we do stage 1.3.
Yeah, insert at tail.
But the parameter is festival when it's supposed to when we're supposed to insert new stage.
Sorry, what?
The parameter for stage 1.3 is festival, but we are supposed to insert a new stage, right? So
in the assignment, so festival has a linked list of stages in it.
Okay, so we
Not
just access
quite.
the,
So what it is, so like
the
current
stage
is
to
a pointer
festival.
to a
Exactly.
node.
Yeah.
And so when we
And
do
then
current
use
arrow next, we're dereferencing
a link list to
And the actual
And by
the
doing that, we
stages, that
actually
is a linked list. So whatever that
And so from
field is
there,
called, I
we can
forgot what the field is called. That's
Um,
like the head
it'd
or
be
the
the
list
same as
variable,
like
but it's already inside
I don't
another
know
struct.
if adding one to the
So
address.
today we're just dealing with individual
Like
linked
separate
lists,
to address.
but in the assignment, those linked
Be
lists
adding one like
are interacting with other variables. Yeah. So I'll be back.
I guess it would be in that sense. No, so like do you mean backwards in the linked list? So the nodes in the linked list are all like separate in memory. And anytime we can do -1 if we have a contiguous amount of memory, like so the linked lists, the way that they work is that we've got all these nodes randomly scattered around in memory. And so all of those nodes also contain an address to the next node. So if we were to just do -1 from the address of the current node, it's just going to be some random part of memory. It's not necessarily going to be the node. The only way to get back, backwards is if we somehow get the address of the previous node.
Is the one that let's say the last one's that has I know that like so and then the end
Conversation on right now.
so do you know that we're at the last okay, actually yeah. Are you sure?
Sorry about that.
So just to be right? Yes. So we're saying
Did you go through the trading?
Handing it out. And then random no one came. Oh no, I don't think right now. I think it was one before. But we have help sessions almost every day.
Every day at this time, I can go there.
It's not necessarily this time. You can check on the course website. Do you know how to look at the help sessions? So today there's one.
Hi.
So with the snake assignment, right?
Yeah.
There was a change log of this, the Apple behavior here, right? That happened on the 17th of October.
Okay.
And was there an announcement about this anywhere, or was this just sort of? Because what ended up happening was like I was reading through and I finished this section on the 16th. And I read through and I was looking at like the snake, like you've got its path, and I realised it doesn't auto test for if you like eat a split apple, well, a reverse apple and then split apple. And I was like, oh, okay. Then I looked over it and it just said the whole segments. And I had not, I don't know, there wasn't anything at the time, I don't think.
Just email the course account and CC me,
Yeah.
and I'll make sure that Okay, let's just go over that one more time, and then we'll move on to inserting in the middle. So I'll do and this is what you've got to get used to doing, thinking of what cases do I need to check with this thing. So you'll always need to think, is this going to break if my list was empty? Now, if we look at something like print list, that didn't break if our list was empty, because if the head's null, cur will be equal to null. But then we just check, is cur equal to null? That's fine. That's not going to crash anything if it was equal to null. So print list worked without us even having to think about it. But anything where you've got a current next, if you're not checking whether current's null before that, that's going to crash. So insert at tail, the first time we were calling it, our new list was empty, head 2 is equal to null. And down, and that's that's the variable in the main function. In the inserted tail function, we were passed in a value of null and I think 0. So our head in this function was null, our current was null, but then we made some kind of new node with create node. And this would have been at some address. Let's make up a fake one for now. And we would have, create node would have put the data in and set this to be null. Which is great. We've made our new node and we've checked, is current equal to null? Yes, yes it is. So we're basically, we know the list is empty already. So now we just make head point to this new node. So head will have the value basically OXF0, right? It's just a pointer. It will have the address of this new node. And then that's all we're going to do. That's our whole list. And the reason why we have to return it is this is done on the copy of the address of the head of the list, right? We've updated our head variable. The original variable up here isn't being updated, right? That's in the stack frame for main. It still has null. We need to return this address and then store it back in head 2. So it gets updated. It knows where this head of the list is. So when our function ends and all these variables get destroyed, the variable back in the main function knows, this is the new head of the list. All right, that's why we need to return it. We will need to do this anytime our function basically could possibly change the head of the list. All right, the other case is, imagine we've got stuff in our list. And we're trying to insert something else. So the first thing we're basically doing is, and I'm just recapping, we're setting current to the head. We're creating a new node with whatever value we wanted it to have. And it will be pointing to null. And then current isn't null in this situation. We've got nodes in the list. So we'll be doing this thing to find the last node. We'll be saying, is current next equal to null? No. And we'll be moving current along by saying current equals current next. Eventually, current will be at this last node. The next one is null. This loop finishes. So now we've found this last node. And once we've done that, we just connect it up to our new node. So current next right now is null. We don't want that. We want current next to be this new node. And that line there links up the new node to that last node on the linked list. All right. Yep.
Can we make the head to a malloc in the main, or is that against style?
We were asked if we could make head to a malloc. Basically, there's lots of things you can do. The way we're doing it now, yeah, you could. Well, not a malloc, but you could pass in a pointer to the pointer. But we don't really want to go into pointers to pointers. The other thing is, like in the assignment, instead of just having a variable on its own that is the address of the head, that variable might be in another struct. So there are different things that you can do, but for now, I don't want to make this any more confusing than it already is. Yep.
Would it be better to think of current next conceptually as pointing to the arrow? Sort of like the arrow to the next node, if that makes sense?
Yeah, current next is like the arrow to the next node. Yep, that's right. And then also though, what's there? If current, when you change current next, you're changing that arrow. When you're checking what it's pointing to, you're checking, yeah, is it pointing to a node or null? Okay, so that's inserting at the end of the list. And if we do that and it works, we've created two beautiful lists with some numbers in them. Yay. So I'm just talking about different cases. This is all stuff we just went through. Yeah, now we want to be able to insert anywhere. To start with, we're going to try inserting into the middle of the list. Now, there's all sneaky kinds of ways you can find the middle of the list without counting it first, but we're just going to go through and find out the size of the list. So for our step one, can we write a function that can tell us the size of the list? Because then if I want to insert it in the middle, I'll just go sort of halfway through the list. I'll find the length and go halfway. So let's just think, how can we write list length? It's just going to return an integer. We get passed in the head of a list, and it's going to tell us how big this list is. Because the way we're doing it, the only information we've really got about our list is that pointer to the head. We're not storing another variable keeping track of the size for us. We have to go through and count it. So if I've got a list and I'm given the head of this list, how am I going to work out how big it is? I don't know anything but where the beginning is. Yep.
Have a while loop that jumps to each node and then count each node until you reach null.
Yeah, exactly. Have a while loop that goes through each node and keeps a counter of it until we reach null. Yeah, it's just basically a traversal. We want to go right through the list. So we can have some sort of counter. Well, I mean, we could call that length or size or something. I've just called it counter. That's okay. And we can say current equals head. So we've got current pointing here. And yeah, we do our while current is not equal to null. Current equals current arrow next. But at each point, yeah, we just increment our counter. And at the end, we return the counter. So in this example, current gets set to there. Counter will be equal to 0. Is current equal to null? No. So we increment our counter and we move current along. Is current equal to null? No. We increment our counter, move it along. Is current equal to null? No. We increment our counter, move it along. Is current equal to null? Yes, we're done. And our counter now knows how many nodes are in the list and returns it. Okay, does that kind of make sense? So we're just traversing it and keeping track of how many nodes we go to. And that's the length of our list. All right. Now, just to see if this works, before I print my list each time, I'm just going to print the length, at least for my second list. List length. Because do we think this is going to work for all cases? Is this going to be a problem if we've got nothing in our list? It shouldn't be, because if we've got nothing in our list, head will be null, current will be null, but we're checking, is current equal to null? And if it is equal to null, we're just not doing anything in the while loop and returning our counter, which should still be 0. So it should work. But, you know, we'll find out. So, oh, I didn't do it in the loop. So we didn't find out. Okay. Yes, length 1, length 2, length 3, length 10. It looks like it works. All right, but how is this going to help us? We're trying to insert in the middle of the list. Well, in order for us to insert in the middle of the list, we've got to go through the list and stop when we kind of get to the middle. And that's where we're going to insert something. So in this case, if I was inserting in the middle, I would want to create a new node, and I'd probably want to put it in here, right? That means this new node would be at the middle. Does everyone agree? Now, we often in computing start counting at 0. Let's just say that. But we want to stop just before we kind of get to the middle. So if my list is size, in this case 4, 4 divided by 2 gives me 2. We want to stop just before node 2. So just one before, because we want this new node to be node 2. But you know, it doesn't matter if you were off by 1, you'd see it and you'd juggle it accordingly. So now we're just going to have a while loop that counts along where it's up to and basically stops around halfway. Then it's going to try and attach this new node. So our loop, again, we have some sort of current that's traversing through, and it's going to go till it's sort of 1 before the middle, right? That's what that while loop is saying. And it's doing a counter again, so it knows what node it's up to. So it's counting till it's halfway. Now we want to insert a new node. So we've got a new node, but now we've got to connect it up. How are we going to connect this new node up? What do we want to come after this node? So I've got a new node here. What do I want after it? So I want, if I'm putting it in the middle, I want the one after it to be this node here. Does everyone agree? How do I do that in code? So this is called new node. What's this member called? If this is new node, this is new node arrow data, this is new node arrow next. So I want the next one after this new node to be this one here. How do I know where this one is? What's that? It's not the current node. Yeah, it's current next, that's right. So if this is current, this is the next one after current right now. Does everyone agree? But I want it to be the next one after the new node. So my code's going to say, make the next one after the new node be the one that's the next node after the current node. So right now that's the one that's after current, but I want it to be the one that's after my new node. So right now both of them are saying that's the next node. So now we have to update where the current one is pointing. What should be next after the current node now? Yep, the new node. So now I say current next equals new node. So this first line is setting this connection here. It's saying the next one after the new node should be the next one after the current node, which is this. Once we've done that, we can set this link, right? And say, well, now the next one after the current one's the new node. And then we've set both of these connections up, and that new node's in the middle of the list. Does everyone agree? Now, things that can go wrong. So imagine if you did these lines of code the other way around. So imagine if the first thing you did was connect this to here, but you haven't connected this yet. So imagine you did this line first. You go, okay, the next one after the current one is this new node. What have you done now? Yep. Yeah, we've lost the address. So we had the address of this node here. We've overwritten it. And now we don't have anything in our code that has that address. So if we do it in the other way around, we do it this way, we put this, oh, I need to go back to the slide. If we do it the other way around, yeah, we put this into here first. Then we can overwrite this one and make it point to here. So sometimes the order you do things in with linked lists can break things because you're just overwriting addresses that you're going to need. So when we look at the code, we can see we don't want to destroy this and then need it. Like, we need this and then we can destroy it. Anyway, so these things can trip you up a bit. But basically, wherever we're inserting our new node, we're doing our malloc and we're just somehow connecting a few pointers or next things around, etc. So let's try and put this together. Now, do we need this case? And I might change this to head equals null. It's the same thing. So instead of finding the last node, we're going until we need a counter. So let me say counter equals 0. And we need to also find the length, which I called size on the slide, but I'll say list length. Pass in my list. So I've got the list length. I've got a counter. I might move this into here. Actually, we don't need to do that if our list was empty. We don't need a counter. We're trying to find basically the one before the middle, or where the middle would be. So we're going up to the size divided by 2 minus 1. Okay, and each time we're incrementing our counter and we're moving our current along till it gets to about middle. All right. And let's just draw it again. I'm going to have my current here. I'm going to have my new node here. I want new node next to point to the one after current. So I'm going to say new node next equals current next. There we go. And then I want the one after the current to be this new node. So I say current next. Equals new node. Does this look right? So I've got a special condition for if there's nothing in there, because maybe we don't even, yeah, we would need that. We can't do all this current next and all this stuff if there's nothing in our list. So we have that special case for an empty list. Otherwise, we count along till we get approximately halfway and connect it up. Does it work? Let's find out. Oh, I haven't used it, but it compiled, that's good. Insert at middle. Now, if we have a look at the list we've already got, if I wanted to insert something in the middle of this list, like right at the end, it should go in here. So if I inserted 99, it should end up in here, right? 0, 1, 2, 3, 4, then 99, then 5, 6, 7, 8, 9. Okay. Oops. I know I'll put 99 in there. And then I'll print it out and see if it at least worked in that case. Did it? Yeah, the 99's in here. Right, so we were able to insert in the middle in that particular case, yep.
Could you just explain the condition at the bottom with like the size?
Now, the size, let's just go through it. And the thing is, whenever we're talking about the middle, there's some cases where there's no middle, right? If I've got a list with, oops. If I've got a list like this and I want to insert in the middle, where's the middle? Where would I put it? There's no real answer because this is in the middle. If I put it here, that's not exactly the middle. If I put it here, that's not exactly the middle. So for something like this, you would make a decision and think, I don't even care. Either one will do, it's approximately the middle, or there might be a reason that you should do one or the other, or you might be told you have to do one or the other. And in this case, I believe it's going to be in here somewhere. But anyway, let's go through what's happening with a case where it's easier to see what the middle is. So let's say I've got 1, 2, 3, 4, 5, 6. I've got 6 things. The new node should definitely go in there. But originally when I find the size of this list, the original list, it's going to be 1, 2, 3, 4, 5, 6. So that'll be 6. And then size divided by 2 gives us 3. And basically our loop is going up to counter is less than 2. Because our counter starts at 0. Now we could reprogram this and make the counter start at 1, but in computing we often have things starting at 0, so there we go. And we can think of this as node 0, 1 and 2. So originally current is here, I'll call it car at the head. And then we're incrementing our counter. Our counter would now be 1, and we move car along to the next one. 1 is less than 2. So we keep going through the loop, we increment our counter, and we move car along to the next one. Now we've got 2. 2 is no longer less than 2. We're going to stop. And that gives us this node just before where we want to insert it. Yep.
So 0 is not the head, right? You would have something pointing to 0. Just out of curiosity.
Sorry, that would be the head. Yep, the head. So we've got the head, and these indexes, unlike arrays, they're not built into the linked list. We're just deciding that I've got a counter that's got to count up about halfway, and I'm going to think of this as the 0th one, the first one, the second one. You might program it differently. You might have your counter starting at 1, and then your loop might have a slightly different condition. But the point is we've got to somehow get about midway to add that other node on. Okay. Yep.
Would there ever be a situation
Yeah, you could have to replace a node, or tomorrow we'll be talking about deleting a node. You might have to find the middle node and delete it, or you might want to do that, you know, rather than someone just telling you that you've got to do it, like sometimes in courses. In real life, you might need to do that. But also, we can adapt this code, which we may not have time to do today. We can adapt this code to insert a node at any position. So here we happen to insert the node in the middle. We want to be able to sort of make this even more general and say, I want you to insert a node at position 4. And that might mean that once we insert it, this new node should be position 4, right? Okay, and we can just extend this code that we've written to do that. Do we want to try it now? Or are our brains fried? Okay. Maybe we might leave it till tomorrow so your brain has had time to cope with inserting in the middle. Just one more thing though. We didn't really test this very well. I just tried one thing to see if it worked. I'm going to make a third linked list that's empty. And I'm going to insert something in the middle of that linked list and just check that it does work. I mean, it does work. It should work. We hope. But let's double check. We should always check these things. Yep. We end up with a list that now is length 1 and has 42 in it. So we should check a few more cases. Okay, but I might leave that for you guys to do. So tomorrow we are going to talk about inserting at any position in the list. If you're keen, you can try and look at that code for the middle tonight and see if you can work it out. But the other thing we want to think about is, what do we need to check? So we're always going to need to check, does this work if my list is empty? But now you're trying to insert nodes at any position. So you're going to be wanting to think, well, I might already have a list. So when we're inserting at the middle, we mightn't have come up with these cases, but if we're saying, I want you to insert at position 0, the new node would have to go here. So you'd want to check, does that work? You could be saying, I want the new node to go at position 0, 1, 2, 3, 4, 5. So the new node might have to go here right at the end. You want to check, does that work? What if the person using it says, put it at position -1? Does that crash your program? What if they say, put it at position 5000 and there's no such node? Do you just try and go through your program and crash it? Like, we want to check all these different cases. And yeah, also, what if there's one node in the list already and I want to insert it at the beginning? Like, do these cases work? So tomorrow when we code this up, we'll code it up without thinking too much, and then we'll go check all these cases, and then we'll have to try and fix them, because these are things that happen in real life. Once you do a lot of programming with these things, you'll see ahead of time what you might need to think about, but often there's something you didn't consider that will pop up and your program's going to crash. So we'll go through that tomorrow. We'll just modify the code we've got for middle. We only have to make small modifications, and then it's nearly right, but then we'll see a few cases where it's going to crash. And you've got to get used to having a program crash and not panicking. I don't know if anyone panics when their programs crash, but I used to panic and think, oh no. But it's like, you know, we'll work it out. So that's it. Tomorrow we'll do that, and then we'll do deletion. So thanks everyone for coming. I know it's hard on your brain, and 2 hours is a long time as well. See you later.